Recording in progress.
Okay, so first thing what I want to talk about, it's consider, and I will start with the same problem that we talked about. Now say I have this spring mass damper system. So this is the mass, this is K, and this is spring. So you have stiffness K, then damping coefficient C, and mass M. So K is the stiffness, M is the mass, and C is the damping coefficient. Now we have to derive the differential equation of motion. And if I apply Newton's law, summation of forces is equal to mass times acceleration. What I get is I get K times X minus C times X dot is equal to mx double dot. That leads to mx double dot plus cx dot plus kx is equal to 0. Now what I want to do is I want to find out the solution of this differential equation. So the objective here is to find solution of differential equation. So before I actually start working out what this is, I want to understand from you, what do we mean by the solution of a differential equation? What do we mean by solving an equation? So I give you a very simple example. Say if I write an equation, something like this, x plus y is equal to 3. Okay. I can say this is an equation and the solution is x is equal to 0, y is equal to 3. Solution is x is equal to 3, y is equal to 0, or the solution is x is equal to 1, y is equal to 2. Everyone agrees? What that means is if I substitute this value here, if I substitute this value here, left hand side and right hand side is equal. That's what we mean by the solution of a solution of an equation. Same thing applies to differential equation, which means if I substitute potential value of x, if I substitute potential value of x dot, and if I substitute the potential value of x double dot in this equation, and if the left hand side is equal to right hand side, then that is the solution of a differential equation. So what is the solution of a differential equation? Solution of a differential equation is a function. That function is f, which is given as fx of t. It could be a sine, it could be a cosine, it could be anything. It could be a series, it could be a Chebyshev polynomial, it can be anything. And what I'm going to do is I'm going to find out f dot, which is dxt by dt, and I'm going to find out f double dot, which is d2x by dt square, and I substitute these three things in the equation that I have over here, and if my left hand side equals to the right hand side, then everything is perfect. So which means the left hand side is equal to right hand side and things make sense. And what I want to do is I just want to show this case. I will work out a general case, but imagine, consider if C is equal to 0, then my equation becomes mx double dot plus kx is equal to 0. And I'm going to assume x is equal to a sine square root of k by m t plus b cosine square root of k by m times t. And I'm going to differentiate this x dot. So if I differentiate this x dot, I land up with a sine becomes cosine, square root of k by m comes out, cosine square root of k by m t plus cosine derivative becomes sine. So this becomes minus b sine square root of k by m t square root of k by m. But this is x dot. What I need to do is I need to differentiate this equation again. So I need to redifferentiate. I'm going to do x double dot, and x double dot, check this out. First term is a square root of k by m cosine. So this is going to become a k by m minus sine square root of k by m t plus, then I have this b sine, so that's going to become minus, so this will become minus b k by m cosine square root of k by m t. Now please understand, our original equation is mx double dot plus kx is equal to 0. So what I'm going to do is I'm going to substitute this guy over here and the x value that we talked about over here. So if you look at the system, I'm going to just do this calculation one time. Minus a k by m sine square root of k by m t minus b k by m cosine of square root of k by m t plus, don't forget we have k floating around here, a cosine, so let me see, how did I do it? A sine, so a sine square root of k by m t plus b cosine square root of k by m. Now can someone tell me, if I perform this addition, what do I get? If I perform this addition, what do I get? Can you see that this guy cancels with this guy and this guy cancels with this guy, which means we have 0. So what it means, the left hand side of the equation is equal to right hand side of the equation. That means whatever solution we assumed is the correct solution for this differential equation. And if I were to plot this solution, it's a combination of sine and cosine. So this is going to be something like this. And that is very obvious. So if you have a simple spring mass system, and if you pull this, it will go back and forth, back and forth, back and forth, back and forth, and so on. So this indeed is the solution of this differential equation. Now the problem comes is, let's look at the original system that we talked about. The original system has this damping floating around. So the equation that we are trying to solve is mx double dot plus cx dot plus kx is equal to 0. Let me tell you, if you substitute x is equal to a cosine square root of k by m t plus b sine square root of k by m t, this is not going to work. So you will notice that the left hand side will not be equal to the right hand side. So this is not the solution of this system. Are you with me so far? Now, at this point, I want to tell you the most important thing that you probably studied in the differential equations class. How many of you have taken a differential equations class? Linear differential equation. Everyone must have taken differential equations or calculus 3 or calculus 2 class, right? Okay. So what is the most important thing from that class? And I'm going to tell you that in 5 minutes. And that's the only thing that you guys need to remember for the rest of your life. Can someone tell me what is the crux of the differential equation course? Can someone huh? You did blocks diagram in differential equation class? Simplify equation. Okay, so before I actually give you the answer, I just want to ask you, what do you remember from the differential equation class? Anything? Nothing? Okay, here is the only thing I want you to remember from the different, and this is very useful to solve any linear differential equation that does not include forcing. For forcing, understand large data set from only a small given data set. I said differential equation, not machine learning. I don't know if or data analysis class, but anyway, they probably that's the correct answer. But so here is something I want you to remember. I want you to remember x is equal to e to the lambda t. Lambda is an exponential function. What is the beauty of the exponential function? Exponential function, if you use Euler's identity, e raised to lambda t is going to be cosine lambda t plus I sine lambda t. What that means is this is a periodic function. Oh, check. Yeah. This is a periodic function, so is this. What it means is if I take the derivative of x dot, I get the same thing. If I take the double derivative of x dot, I get the same thing. The only difference is x, x dot, and x double dot are scaled. Everyone understood this? X, x dot, and x double dot are scaled. Whenever you see a differential equation, say I give you this differential equation, and I'm going to start with something like this: x double dot plus, so mx double dot plus cx dot plus kx is equal to 0. This is the differential equation. And what I want you to do is, I want you to solve this differential equation. So if I ask you to solve this differential equation, what you should do is you should substitute this x into x here, x dot into x dot here, x double dot into x double dot over here. So what would happen is your equation will now become c a lambda e to the lambda t plus k a e to the lambda t. Are you with me so far? This is the only thing that I want you to remember. And then solve this. So you would observe that a is here, a is here, a is here. So a gets cancelled. You agree with me? A gets cancelled. And I have this equation m lambda square plus c lambda plus k e to the lambda t is equal to 0. Are you with me so far? Now, e to the lambda t cannot be 0. Why it cannot be 0? Because if e to the lambda t is 0, which means our basic assumption that we started with, x is equal to 0, is going to be 0. Everyone understood this? So e to the lambda t cannot be 0 because we assume that x is a non-zero solution. So this is our basic assumption. So this is the basic assumption that we are starting with. So what that means is this guy m lambda square plus c lambda plus k has to be equal to 0. Do you agree with me? Now here, please understand, m is mass. So this is a constant. C is damping. This is a constant. And K is stiffness. This is a constant. Do you agree with me? These three are constants. Which means the only thing that can be 0 is lambda. And this is a quadratic equation. So this is a quadratic equation. So I would find the roots of lambda, lambda 1, comma 2. There are two roots, will be minus b plus minus square root of b square minus 4ac divided by 2a. Are you with me so far? And this is the most important equation to study. And I'm going to look into this in a little bit more detail. So what we have found out lambdas, lambda 1 is equal to minus c plus square root of c square minus 4ac divided by 2m. Lambda 2 is equal to minus c minus square root of c square minus 4mk divided by 2m. One thing I want you to understand, that these are all constants. So once you substitute these values, you are gonna get numbers. Those numbers you will substitute in this equation, and boom, that is the solution of your differential equation. You take any differential equation, this is the way to solve that differential equation. Everyone understood this? This is the crux from the differential equation class. Now these lambdas are called eigenvalues. Now let's look at these eigenvalues in little bit detail. Okay. Now, as you know, let's look at m, which is mass, k, which is stiffness, and then c, which is damping. Now I want to discuss three cases. So the case 1. In case 1, imagine my c square minus 4mk is equal to 0. If my c square minus 4mk is 0, that means my lambda 1 is equal to lambda 2 is equal to minus c divided by 2m. Do you agree with me? Which means two roots are negative. These are also called as roots. They are negative, which means the solution would be decaying. So the solution is going to be something like this. Do you agree with me? Now let's understand this case number 2. Case 2, where c square is less than 4mk. If c square is less than 4mk, can you see that the square root of c square minus mk will have a negative part, which means the roots lambda 1 and lambda 2 will be complex conjugates with negative real parts. What that means is you're going to have a response which is decaying, something like this. You will have negative the conjugate parts. So what will happen is, because of conjugation, you will have the periodic coefficients solution, and it will be oscillated. The last part is case 3. Is c square is greater than 4mk. If c square is greater than 4mk, then again you are going to have an overdamped system. So c square is greater than 4mk. Now here I need to tell you something. C square is greater than 4mk. What that means is square root of c square minus 4mk will be less than c. Do you agree with me? which means these roots lambda 1 and lambda 2, lambda 1 and lambda 2 will be different but with negative, and lambda 1 and lambda 2 will not be same, but lambda 1 and lambda 2 will be different but negative. So in this case the response is going to be like this. Now these three things are super duper important, and I want you to understand this very, very carefully, because the problems that we are going to discuss will involve referring to these concepts. So this system is called as critically damped. This system is called as underdamped. And this system is called as overdamped. Are you with me so far? So I will wait for a minute, because this is a very important concept that is not emphasized, unfortunately, in differential equations class. But this is the only thing that you have to remember. Once you understand, if you want to solve a differential equation, substitute e to the lambda t into that differential equation, and then just find out the values of lambda, and whatever you get, plug that back in, and boom, that is the solution of differential equation. Now next thing which I want to talk about is, imagine a very hypothetical case. Imagine very hypothetical case. If your damping is negative, assume damping is negative. So what do I mean by damping is negative? Damping is negative, and I want you to understand, this guy which was negative becomes positive. This guy that was negative becomes positive. Do you agree with me? If damping is negative, the actual coefficient C has a negative sign, which means these lambda 1s and lambda 2s will have positive real parts. Do you agree with me? What is the implication of having positive real parts? If you have a negative real part, can you see the system response is decaying? System response is decaying. System response is decaying. If you have a positive real part, then the system response is going to increase. Do you agree with me? That is undesired, that we don't want. So basically, if you have positive real parts, then the system response will be expanding, it will be increasing. So the system would become unstable. Are you with me so far? Everyone with me so far? So system would become unstable. Now next case which I want to talk about is, imagine, so we saw that if in mx double dot plus cx dot plus kx is equal to 0, if c is negative, then the system is unstable. Why? Because eigenvalues or lambdas will have positive real parts. Now what happens if k is negative? What happens if k is negative? Please go back to the same equation that we talked about. If k is negative, do you agree with me? The term under the square root sign will be greater than C. Once again, if K is negative, square root of C minus MK will become square root of C plus MK. Do you agree with me? Which would be greater than C? Do you agree with me? Are you with me so far? What that means is your lambdas will become positive. And if lambdas become positive, the system is unstable. Everyone with me so far? So what is the takeaway? Takeaway is, if you have an equation mx double dot plus cx dot plus kx is equal to 0, system could be underdamped, critically damped, or overdamped. Are you with me so far? However, for some reason, and this is mass will never be negative, but if you land up with this equation, or if you land up with this equation, or if you land up with this equation, system is unstable. Are you with me so far? Online students, this is a super duper important point, and I want to repeat this once again. If you have a linear differential equation in this form, 3 types of responses are possible. If you have a differential equation in the form that is shown over here, so I'm going to call this 1 and I'm going to call this 2. If differential equation is shown in the form given by 2, then your system is going to be unstable. Are you with me so far? Online students, did you understand this? This is a very, very important concept. And this is the crux of your differential equation course. Now, I want to take one simple example. It's actually a trivial example, but still I want to do it before I start solving complex problems. So here is the system, and I will stick to my argument. I will say if you have x dot is equal to a x, I'm going to substitute x is equal to maybe capital A e to the lambda t. X dot is equal to a lambda e to the lambda t. So you will have a lambda e to the lambda t is equal to a capital A e to the lambda t. This a will vanish, and now I have this equation which is lambda minus a e to the lambda t is equal to 0. Same argument, e to the lambda t cannot be 0, because if e to the lambda t is 0, that means x is equal to 0, which means we are dealing with a trivial solution. That means this guy has to be 0, which means lambda is equal to a. Now this is the same thing what we did, remember, in the last class, but now I don't have to do any integration, anything like that. I got the solution. I would say my solution is x of t is equal to a e to the at. Are you with me so far? Boom. No integration necessary. You remember I worked out this problem in last class, and then I had to take on the left hand side, right hand side, and then integrate the ln function and then go through this mathematical jugglery. But if you just remember this, what I have done here, problem solved. Are you with me? Now, the power of this technique is not in the solving these simple problems. Here is where this technique shines. Imagine that you have a nonlinear system. Nonlinear system. You have this nonlinear system, and this nonlinear system is given by equation, say mx double dot plus cx dot plus kx plus kx square is equal to 0. So this is k1 and k2. Clearly, it is very difficult to solve this equation with the technique that I've shown you. Okay. But what I want to know is, I want to understand that whether this system is stable or unstable. So the simple question is whether this system is stable or unstable. What I'm going to do is, I'm going to perform something called as linearization. And what happens in linearization? In linearization, this nonlinear terms would go away. And once I linearize, this equation is going to become mx double dot plus cx dot plus k1x plus 2 times k2 x bar, which is, and then x is equal to 0. And depending upon what the initial operating point is, this is the operating point. This is how that, so this could be, for an example, if you were to linearize this about 0, then you will see that this equation will become just a linear equation. If you try to linearize this about -1, -2, these values would slightly change. So now what the takeaway point here is, depending upon where you are operating, this equation could become of form 1 or could become of form 2. Are you with me so far? And I want to emphasize this because this is a very, very important part. So imagine you have a nonlinear equation, nonlinear system. All systems we deal with are nonlinear. And you want to find out, so the very fundamental question that once you see a nonlinear system is whether this system is stable or unstable. Which means if I give it a push, is it going to go anywhere or is it going to come back to where we started? So that is the key question, whether this is stable or unstable. So what do? We linearize. And once we linearize, we get this linear equation on the right hand side. This is the approximation, the linear approximation of nonlinear system. Do you agree with me? In this equation, there is this x bar. X bar is the operating point, and I will carry out this linearization and I will show you how this equation comes into existence. But before I go there, I want you to understand that this is the equation that I got. Depending upon what is the value of x bar, which means where I am linearizing. If I'm linearizing around 0, which means x bar is 0, and I just have an equation which is given by equation 1. Do you agree with me? If I'm linearizing, if my x bar, that operating point, is 1, then I'm linearizing, then that equation still is of the form 1. But imagine I'm linearizing about -100, then what would happen to the equation that I have shown over here? If I linearize it about minus 100, then this equation will become of the form 2 and the system becomes unstable. Are you with me so far? You may not believe me, but here is what exactly is happening. Imagine you have a pendulum. You have this is the pendulum. This is the pendulum. If the pendulum is like this, and I swing this pendulum, do you agree with me that this pendulum is stable? It will come back to its original position. Do you agree with me? Imagine if I have an inverted pendulum and if I displace this, what would happen? What would happen? It will drop down. So this is stable and this is unstable. Now, same point, same pendulum, nothing changed. The pendulum is stable. So if you maintain it like this, it is stable. If you maintain pendulum like this and then everything is perfectly aligned, it is stable. But as soon as you push this, give a perturbation, it becomes unstable. So what changed? Operating point. And why did the pendulum behave like this? Because the pendulum is a nonlinear system to begin with. Are you with me so far? Now I want to do a detailed analysis on this, but before I do this analysis, I want you to take a deep breath and quickly review the concepts that we talked so far. These are super duper important concepts. Once you understand these, you understand dynamical systems very well, differential equations very well, vibrations very well. Here is the basic point. For any dynamical system described by linear differential equation with constant coefficients, this is the technique to solve x is equal to a e to the lambda t. Differentiate, double differentiate, triple differentiate. How many times that x has dotted, differentiate those many times. Equate left hand side and right hand side. Find the values of lambdas. What are lambdas? Eigenvalues. Eigenvalues. Once you find whether those eigenvalues are zero, eigenvalues have negative real parts, or eigenvalues have positive real parts. If the eigenvalues have positive real parts, the system is unstable. If the eigenvalues are zero or they have negative real parts, then the system is stable. Everyone understood this? That is the key concept. This is true for linear systems. For nonlinear systems, just by looking at the system, you cannot predict about the stability of the system. You can't just look at the differential equation and say, hey, this equation, this system is stable, this system is unstable. So what is the process? We pick an operating point. We linearize that system about that operating point and then see what do we get. And once you linearize that system about an operating point, you are going to get a linear approximation of that nonlinear system. Do you agree with me? That linear approximation could be of form 1 or it could be of form 2. Do you agree with me? If that linear approximation is of form 1, you would say that nonlinear system is stable at that operating point. Everyone understood this? If your equation is of the second form, then you would say that nonlinear system is unstable at that operating point. Everyone understood this? Online students, did you understand this super important concept? Okay, never ever forget this. Okay, please do not forget this. This is super duper important. Okay, so what I want to do is I want to actually take a very simple example, and some of you may ask me, hey, linearization, Taylor series approximation, uh, I'm not good in math, so what do I do? So I want to show you Redcar's method of linearization, which is a method that you can do with high school algebra. Okay, so I'm going to do this with an example. So how do we find if nonlinear system is stable or unstable? And let me take this example. Say I have this pendulum. The pendulum equation is theta double dot plus g by L sine theta double dot plus g over L sine theta is equal to 0. Do you agree with me? This is the equation of pendulum that we derived in last class. This equation is nonlinear. Are you with me? This equation is nonlinear. Now, what I want to do is I want to look at two cases. Case number one is when this pendulum is down. Case number two, when this pendulum is up. So when pendulum is down, what is my operating point? When my pendulum is down, my operating point is theta is equal to 0 degrees. Do you agree with me? What is my operating point when pendulum is up? Is 180 degrees. Do you agree with me? Because I'm gonna, so this is my datum. So from here all the way over here. So this is 180. So what I'm going to do is I'm going to do the linearization. So linearization is I will take this sine term and then actually I would do the derivative. So basically sine theta is equal to what I need to do is I need to do the operating point, which is theta minus plus cosine theta. And I will have delta theta. So I would substitute these equations in the equation that I have. So theta double dot, I'll write down the Taylor series expansion first. F of x is equal to f of x at x is equal to x naught plus partial or full f df by dx delta x and df by dx at x is equal to x naught. So I'll write this equation down. F of x at x is equal to 0. If my x is equal to 0 is equal to 0, this equation will become sine of 0 plus df by dx, which is cosine of 0 multiplied by delta x, which is delta theta. And then what I would do is this that means sine theta is going to become delta theta. So this at x is equal to 0, my equation will become, so theta is going to be substituted as delta theta plus g over L. Delta theta is equal to 0. So this is the linearized equation about theta is equal to 0. Now what happens when I linearize about theta is equal to 180? When I linearize about theta is equal to 180, sine theta will become 180, cosine of 180 becomes minus delta theta. So your equation is going to become delta theta double dot minus g over L delta theta is equal to 0. Are you with me so far? So please understand that this equation, the stability is dictated by this equation and stability is dictated by this equation. Tell me, this equation is of the same form, mx double dot plus kx is equal to 0, and this equation is of the same form, kx is equal to 0. Which one is stable and which one is unstable? The equation here is stable and equation here is unstable. Are you with me so far? So what I'm going to do is I'm going to work out the problems, and when we do the linearization, we are going to look at what is the form of equation we get, and then see if these equations are similar to the equation of type 1 or type 2. If we land up with equation of type 1, the system is stable. If we land up with the equation of type 2, then the equation is unstable. So let me know if you have any questions. Yeah.
How do you get the linearization equation?
Using the Taylor series approximation. Well, I was waiting for this question. Okay, so now I will show you a crude way of linearization. Okay, this is not super duper scientific, but this works. So consider that you have equations. Let's start with something like this. So theta double dot plus g over L sine theta is equal to 0. Do you agree with me? This is the linearization equation. What do we mean by linearization? Linearization means something like this. So you have this function, and what you want to do is you want to find this straight line approximation wherever you are, right? You have to find out the straight line approximation wherever you are. So what I'm going to do is I'm going to find this linearization something like this. I'm going to say theta is equal to theta operating plus delta theta. Are you with me? So what I'm saying is, if I'm at this theta, if I want to go to this theta, what do I need to do is I need to go by theta plus delta theta. Do you agree with me? This is true wherever I go. If I'm here, if this is my theta operating, I need to go by amount delta theta, and this is where I go. Do you agree with me? So what I'm going to do is I'm going to substitute this in the top equation. So theta is equal to theta operating plus delta theta. So theta double dot is equal to theta operating is a constant. Are you with me? So this becomes delta theta double dot. Now what happens with sine theta? So I would substitute sine theta is equal to sine theta operating plus delta theta, right? And then expand. What is the expansion of sine? Sine theta operating cosine delta theta plus cosine theta operating plus sine of delta theta. Do you agree with me? Sine A plus B. This is the expansion of sine A plus B. Sine A cosine B plus cosine A sine B. Right? Now let's consider my operating point. So operating point. So is theta operating is equal to 0. What happens if theta operating is 0? Can you see this sine theta? This becomes 0. Cosine delta theta, and delta theta is actually a very small quantity. So cosine delta theta becomes 1. Then cosine of theta operating is going to be 1. Sine delta theta is a small quantity, which means that will be approximated by delta theta. So now you got delta theta. Are you with me? Substituting all this in the original equation, what do I get? Theta double dot plus G over L theta delta theta double dot delta theta is equal to 0. So the equation becomes stable. For a minute, I want you to think about what happens if theta operating, if theta operating is 180, then sine theta is going to become sine of 180. Then you will have cosine of delta theta plus cosine of 180 sine of delta theta. So sine 180 is 0. Cosine delta theta, since delta theta is small, cosine delta theta is equal to 1. Sine delta theta is delta theta plus 1 This becomes minus because cosine 180 is minus. So you got minus delta theta. That gives you equation delta theta double dot minus G over L delta theta is equal to 0. And this equation is unstable. So this is how you can do a brute force linearization. So what is brute force linearization? Brute force linearization is you have any nonlinear function and it always works. You don't have to use the Taylor series expansion. Any nonlinear function you approximate as the operating point plus teeny tiny deviation around operating point. And that's exactly what linearization is. Linearization is teeny tiny variation about operating point. You cannot linearize throughout the domain. You can linearize only at operating point. So you would have fixed operating point and small deviation. So you would have that small deviation, plug that value into your original equation, expand that function and throw away the nonlinear terms because we don't want nonlinear terms to be floating around in linearization. So that's why what I did is for small angle approximation, cosine of small angles is 1, sine of small angles is that angle itself. Everyone understood this? And then when I plug these equations in, what I realized, when the system, when the pendulum is up, I get the equation for stable operation. I mean, when the pendulum is down, I get a stable system. When the pendulum is up, I get an unstable system. Everyone understood this? This is the crux of linearization. And this is the simplest way you can analyze a nonlinear system. Are you with me so far? Online students, everyone understood? So what I'm going to do is I am going to take a break of 10-15 minutes, and after the break we will come back and I will work out the problems that I promised I'll work out in last class. So we are going to stop here. So here we have a motor. This motor is connected to a shaft and a coupling. So we have this motor. This is connected to the shaft and coupling. Okay, don't know what's going on. I'm gonna try a different app. Let's try this. So this is the motor. It's connected to a pump. The motor is the shaft. Pump. And if you look at the inside of the pump, you would notice that there's an impeller, and this impeller is running in this water that is causing some friction. This is damping. So this is B1, this is K. The speed here is capital omega. Speed here is small omega. The moment of inertia of this impeller is J, and the friction damping is B2. Now what we want to do is we have to perform the complete analysis of this equation, of this system, and finally come up with a differential equation. So step number 1 is what we want to do is we want to find out the value of torque supplied by a motor. So if you think about the torque that is supplied by the motor, so torque is given as stiffness multiplied by change in the angular velocity. So K omega 1 minus omega is the torque that is supplied by the motor. Now we have to find out the torque which is dissipated, and torque dissipated can be written as B1, which is the damping coefficient, multiplied by the differential speed omega minus omega 1 minus T1. This is equal to, actually this is equal to T1 or T. So then what you do is you can use these two equations together. This is actually dt, bit of change of. So I would take the derivative of this guy. So dt by dt, d1 is a constant. Then I'm going to have capital omega dot minus omega 1 dot. Substituting this equation 2 into equation 1, substituting two in one, I land up with dt by dt is equal to minus k b1 t minus k omega plus k capital omega. And for j, I get an equation j omega dot plus b2 omega is equal to t. Because please understand, this is sort of the same equation that we dealt with. This is omega, this is theta. So j theta double dot plus b2 theta dot plus k, in this case k is 0, is equal to t. So this is the equation that we have. So now we have these two equations to deal with, 1 and 2. And now we have to write this equation into state space. And these equations can be written as, I'm going to assume dt by dt d omega by dt onto the left hand side is equal to minus k by b1 minus k 1 divided by j minus b2 by j. T omega plus k 0 f2. So this is how you would do the state variable analysis. So now this is the state space equation, which is written as x dot is equal to ax plus p. This is the first problem. Then let me look at the second problem. P2 so robotic sprayer machine, and this machine is something like this. We have this motor, we have this gear transmission, gear transmission has a flexible shaft that is connected to pump, and there is a paint load. So this is Bm omega m. This is pinion, gear, flex shaft, This is TP, WP, JP, pump, DP. Now, first and foremost, I need to start with some assumptions. Omega of motor, angular velocity of the motor, is change in the angular displacement of the motor with respect to time. Angular velocity of the pump is change in the angular displacement of the pump divided by time. Now please understand, we have a gear mechanism. So what would this gear mechanism do is depending upon the gear ratio. So depending upon gear ratio, so if I call that eta, so you would have basically variation from the input side to the output side. So let me start with something like this. So pinion power is equal to T pinion multiplied by omega pinion. Motor power or the gear power T gear multiplied by omega gear. Now please understand, there is a gear ratio, and gear ratio will give you omega pinion divided by omega gear is equal to R, which is called as the gear ratio. So I can write the equation for efficiency is equal to T pinion R omega motor divided by T gear omega motor. But please understand, R times omega n is omega p, which is output power divided by input power. So this gives me a relationship Tg is equal to R efficiency multiplied by T. So this is one important relationship that we need to consider. So now we have to apply Newton's second law. And once you apply Newton's second law, Tm minus Tg is equal to Jm omega m dot plus Pm omega m. This is the torque, this is the inertia, and this is the damping. Now the next part is, this is applying to the motor. We have to apply the Newton's second law to pump. Tp is equal to Jp omega p dot plus Bp omega p. This is for the pump. And the equation that we have from here, please note Tp is equal to Kp theta m divided by r minus theta p. So this equation is something like torque is equal to torsional stiffness multiplied by delta theta. So with these equations, we can combine these equations and write down. So let me put it this way. You have equation 1, you have equation 2, and you have equation 3. So these three equations, we are going to differentiate equation number 3, and I would get and once you choose the states, so I'm going to assume states as omega m, tp, omega p, and once I find out the steady state, so in steady state all the derivatives are state to 0. So for steady state, all derivatives are stated to 0. You get Tm is equal to T naught omega naught minus omega m divided by omega naught square minus omega m square. And once that is done, what you can do is you can find out for starting torque, omega m is equal to 0 and Tm will become T0. And then if you look at this original equation, what you have to do is you have to differentiate with respect to starting torque, and then you are gonna get an equation. And that equation would tell you whether that that the constant, this ratio delta Tm by delta T naught is positive or negative. And then what you need to do is for steady state, so please understand, for steady state, what you need to do is you need to look at the solution, and you can write the matrix A and you can write matrix B and you can write matrix C, and we assume X is equal to Wm Tp Wp. The control input U has T naught W naught, and the output has Wp TP, KP transpose. And once you do that, your A matrix will be minus B BM divided by JM minus R JM 0 KP divided by R 0 0 1 by JP minus KP minus BP GP B GM 2 by GM 0 0 0 0 1 0 1 by KP 0 and D equal to 0. So that is how you will try to solve this. And the second problem is in principle similar with this problem. First, again, you have to write down the equation. So I'll go ahead and try to discuss this problem. The second problem, or the third problem, what we have is we have a motor, there is a coupling, and there is this cutter. This is omega m. This is Tm, Jm, omega m, K, omega c, and then there is this TL, which is C, omega c. So this is very important. So what this tells me is torque is always going to be positive if omega c is positive, and torque will be negative if omega c is negative. So that is the condition. So we start first, we draw the free body diagram and write the equations using Newton's laws. Jm omega m dot is equal to the torque minus Bm omega m minus dk. It is exactly same as the first problem. Using Hooke's law, dk dot k omega m minus omega c. The last part, jc omega c dk minus bc omega c c wc omega c omega c. So these are the three equations, and we have to use the state vector omega m t omega c And these are the same problems that I kind of briefly discussed in last class and ask you to review. Input vector is Tm and output is Tl. Now we will substitute these equations and then land up with one equation which is given as Jm is equal to Tm minus Bm Tk dot divided by K plus omega C minus T. And then what you need to do is you need to perform the mathematical jugglery, and then finally once you perform this mathematical jugglery you are gonna get a nice equation, and that you need to linearize, and after linearization you are gonna get, so the linearize you will get an equation Jm omega m Tm minus Bm omega m K so K omega m omega C and J omega C is equal to K minus BC omega C minus 2C omega C. And then you can put these in the state space form. So these are the problems. I would encourage you to review these problems, and somewhere there is, from here there are a lot of math steps. You can actually use MATLAB or Mathematica if you are not comfortable in doing that math with hand. So just go through this, and you will use the same concept that we discussed in today's class. And in the last problem, which is about the rocket, actually there is an elevator problem which is also again similar, and then there is a rocket problem that also is similar. So the finally what you have is you have to apply Newton's law. From Newton's law you are gonna get a nonlinear equation. You have to take that nonlinear equation, linearize the nonlinear equation, and finally come up with the state space equation. So this is the basic steps. Newton's laws that will yield a nonlinear equation, then linearize, and then express the equation in the state space form. So please work out the homework problems, and if you have any questions, I will work out those homework problems in class next time. But I just don't want to give you a complete solution, because unless it's not a spectator sport, unless it's like swimming, unless you work out the problem on your own, get stuck, try to figure out reading the textbook, then you learn a lot, rather than I'm just giving you the solution or explaining you the solution. So today also what I did, I showed you the basic steps. The detailed steps are worked out in the textbook, So please follow these steps, and then the homework problems are exactly similar, and I will work out the homework problems in class. So in case if you get stuck, I would be happy to answer any questions you may have. So what I want to do is, I just want to talk about the next part of today's lesson, which happens to be the last part in this chapter. So it's the block diagram algebra. So what is a block diagram? In last class, we looked at the transfer functions. Those transfer functions can be represented as block diagrams. So here, what you have is, you have your transfer function. This is where you have transfer function. And many a times, we are dealing with multiple transfer functions. So for an example, it's not going to let me annotate. So I would just explain using the slides. Sorry about this. PowerPoint is giving me a hard time today. So you have the transfer function. That transfer function is written inside the block diagram. You have certain inputs, you have certain outputs. And if you have multiple systems that are connected either in series or in parallel, you can represent those interconnects using the block diagram. A simple block diagram is something like one input, one output. That is for SISO system, single input, single output system. If you have a block diagram that has more than one input and more than one output, that would be the block diagram for MIMO system, multiple input, multiple output. Now, if you look at the block diagram, typically block diagram would show you how this different block diagrams or how these different subsystems are attached. And you'll see something called as summing junction inside the block diagram. And this is what happens when you have a block diagram that comprises of one or more subsystems. For an example, if you have two signals coming at a summing junction, those get added. If you have two block diagrams that are next to each other, you can multiply. If you have the parallel block diagrams, then basically you add. If you have block diagram shifting, so basically you divide the signal output by the block diagram value and you get the input, and you can actually deal with the signal shifting. Now, for an example, if you look at this, this is a very classic block diagram. You have the input function B, then you have the integrator 1 over S, then you have this output block C, and then the total output, that is Y. Then you have a feed forward component, which is D, and you have a feedback component, that is A. So this is typically a block diagram is written. So B is the control input. So for an example, the differential equation or in state space is given as x dot is equal to ax plus bu and y is equal to cx plus du. That by block diagram is represented something like this. Then the simulation block diagram will comprise of integration block, constant gain blocks, summing junction, and they are used in computer simulations. They are used for analysis. They are used to obtain input output models. Usually these block diagram representations are not unique. How do we construct a block diagram? Block diagram construction from a differential equation, there are multiple ways of doing it. One is something called as the superposition method, wherein what you have is you actually construct the parent system and then you construct the block diagram for the parent system, and then what you do is you have an auxiliary system and you construct the block diagram for the auxiliary system and then combine these two block diagrams. Actually, this method looks a little bit intimidating, but I will explain it to you what this means. So I need to shift to a different PowerPoint. So basically, let me explain this real quick. So imagine that you have a system x dot plus x is equal to u. So to draw the block diagram, what needs to happen is you have to find out the overall transfer function. To find the overall transfer function, you would do something like s square x of s plus x of s is equal to u of s. X of s will be common outside u of s. So x of s divided by u of s is going to be 1 divided by s square plus 1. So your block diagram is going to look something like this, where you are going to have u of s over here, x of s is going to be here. Now a slight twist here is if you have x double dot plus x is equal to u plus u dot. Same procedure. What you will do is s square x of s plus x of s u of s plus s u of s. Take x of s common outside. S square plus 1 x of s is equal to 1 plus s u of s. And then write this equation as x of s divided by u of s is equal to 1. This is 1 plus s. 1 plus s divided by s square plus 1. And then your block diagram is going to look like s plus 1 s square plus 1. So this is how you will do the block diagram. Any questions here? Any questions here? Okay. And there is a way of splitting this. So what you can do is this block diagram can be written as s square plus 1 1 s square plus 1. So when you look at this presentation, you will see these types of tricks used to represent the block diagram. So if you look at this, what they do is they perform the superposition, and then finally they split the blocks so that you can actually represent the block diagram, something like this. And with that, I'm gonna stop here, and then we are gonna do some labs from AP Monitor. So what I want to do is I want to share my screen. And in AP Monitor, so what I want you to do is I want you to go to Control MATLAB, Temperature Control Lab, and in today's class we are going to talk about regression. So can everyone see my screen? Online students, are you able to see my screen? Okay. Now, what we want to do is, in the last class, we looked at coming up with some type of equation, and that equation is based on the parameters, the physics of the system. Now, what we want to do is we can actually use some type of a regression method to find out what the coefficients are going to look like. And this is exactly what we did in our earlier class, wherein what we did is we derived this differential equation. This differential equation comprised of the first order transfer function, and we added this dead time theta p into this equation. Now, if you see the way the method goes is you can actually get the data either from actual model, or you can get the data from the regression tool, and you can actually create a regression based model, a data driven regression based model that can fit into data. And that's what this FOPDT, so first order with date time, first order model with date time does to the regression. And that was your very first assignment. Now what we want to do is, we want to use this technique. We want to use this technique to perform analysis on heater 1. So if you just have one heater, then what you can do is you can perform the first order model with dead time, or what you can do is you can make it a little bit more advanced by putting it into the second order, say, a process with the dead time. So basically what you do is you have this energy balance equation. Then what you do is, from the simulation data or from the actual measurement data, you get the result, or you get the result, and then you use this first order model with dead time, FOPDT, or you can use SOPDT, second order model with dead time, to find out the linear or the best possible approximation. This code is given in Python. So if you know Python, you can actually use this. Or if you look at the linearization example, wherein the second order linearization is done, it will actually show you how the linearization is done. So I would strongly encourage you to take a look at this energy balance parameter estimation for the first order, and that's what we did, and then for the second order. You can do the exact same thing for second two heater systems, but that will be called multivariate regression. Why it would be called a multivariate regression? It will be multivariate because you don't right now you have more than one parameter to perform the regression. And I would encourage you strongly to take a look at this code. I would just go to this MATLAB code, and then what you can do is you can get the data. Either this data can be the sample data or from the estimate data, or you can get it from the simulation, and try to run this code, and then you will see that you can actually generate an approximate second order model. And if you do the second order model with Python Gecko, this is how that model is going to look like. I know you already have one assignment due, which is next week, so I don't want to give you any more assignments, but I would strongly encourage you to review these labs, because we will be doing these labs in upcoming lessons, and these labs will kind of set us up to understand the control. So basically, how do we control a process? How would we use the proportional and integral control? How would we use PID control? And how do we make sure that the system is behaving the way we want? So again, I don't want to give you any homework or assignment today, because I know you already have an assignment that is due next week. But I would strongly encourage you to look at the regression, one heater, two heaters, and then once we come next time, once we meet, I will work out the homework problems, and then I will move on to performing the labs. So when is it due? I think it's due, if you look at the canvas, I updated the date when the project 3 is due. So yeah, project 3 is due on Wednesday. That way, after trying to work out the problems, if you have any questions, I can work out those problems on Tuesday. So I would strongly encourage you to do these labs, because these labs will set us up to perform the the control, the P control, I control, and D control for mechatronics class. With that, I'm going to stop here, and I would be happy to answer any questions you may have.